Okay, so the final online lecture for this series of lectures on rotating non-inertial reference frames will be about writing down Newton's second law for a rotating reference frame. So that is the goal here. And you should note that this process of getting to Newton's second law here in rotating reference frame is directly related to problem 9.20 on your homework number 8. Okay, so let's begin with what we already know. So that is, if we write down Newton's second law in a stationary frame, so S again will refer to the stationary reference frame, S prime will refer to a rotating frame. So this is just F equals ma, which is true for a stationary inertial reference frame. So again, maybe I can write this down. S corresponds to the inertial frame, and S prime corresponds to a rotating reference frame. Okay, so then we already know from working on some, from the rotating vector theorem, we know that, so we know that we can rewrite the time derivative. So the time derivative of the position, or any vector, can be rewritten in terms of the rotating reference frame by this modifying factor here. Omega cross the vector. Now note that in previous lectures I've written this down with the S, with this term on the left-hand side and this term on the right-hand side. That's the difference. That's why there's a difference in sign here compared to what I've done previously. But this is a true statement. So this is how you can write down one time derivative of the position vector and relate it between frames. Okay, so if we take another time derivative, then what do we get? We have, so this is the acceleration in the stationary frame. So what is that equal to? It's equal to, okay, I'm going to write some slightly odd notation here, but this is going to refer to this is just notation. That is, I'm saying I'm going to take a time derivative of this vector with respect to the, and this is going to take place in this stationary reference frame S. So this is just rewriting this thing, okay? But now, when we replace this time derivative with this formula, then we have the following. We have this r dot in the prime reference frame plus omega cross r. Okay, so we need to take this time derivative on both of these. All right. All right. So then, but first, what I'm going to do is, so remember, this thing in square brackets here, this is just another vector. This is a vector that we can consider, and if we're going to, what I'm going to do is take that vector and relate its time derivative in the S frame to its time derivative in the S prime frame. So again, I'm just applying this rotating vector theorem. So we're going to rewrite this as a time derivative in the prime frame, which again gives you, well, it gives you, it's the same thing where you write down first the time derivative omega cross r. So that's the derivative in the prime reference frame, and then to that has to be then modified again by omega cross this vector, the vector in the square brackets, right? It's the same thing I wrote here, except for in here I was talking about r dot. Now I'm talking about the dot of this whole vector instead of just r. So that is cross R. Okay? So that was just one more application of the rotating vector theorem. And now let's see what happens as we go through this. So we have this first term in this time derivative is just a time derivative of this guy. So that is second time derivative with respect to the S prime frame. And now this has two terms in it, so we have to do a product rule on that. So we have one time derivative of, well, let's write this like this. So this is going to be a time derivative of omega. That's the dot with respect to the S prime frame, right? Cross R. That's the first piece in the product rule. The second piece in the product rule is omega cross R dot with respect to the prime reference frame. Okay, now let's handle this term. We have over here omega cross R dot, again with respect to S prime. That's this term. And then we got to do omega cross that term. So that is omega cross R. Okay, so first of all, we can get rid of this term. So omega is a fixed vector, so this term is 0 because omega dot is 0. Okay, so what do we have left then? What we have left is time derivative, double time derivative of R and S prime. Then this term is the same as that term, so we have a plus 2 omega cross the velocity with respect to the S prime frame. And then we have this omega cross R term. Okay, so we're almost there. That is, we've related the acceleration in the stationary frame to the acceleration in the rotating frame plus two modifying terms here, so that make this transformation between the rotating and the stationary frame. Okay, so now I'm going to erase some of this so I can rewrite the answer up here. Okay, so if we replace this acceleration in the, well, let me rewrite this one time. That is, so we have, so I'm going to rewrite this. So this is on the left-hand side now, the S prime derivative, and we have the acceleration in the stationary reference frame minus, so I just moved this term and this term to the other side of the equation, minus 2 omega cross R dot, and that's in the S prime frame, minus omega cross R. Okay, and then this term, well, let's multiply through by m as well. So this is m. Let's stick an m in here, and an n on this term as well. Now we can replace this one. That's the forces. That's the forces, the actual forces that are acting on whatever particle is located at position r. So that step, replacing this with F, is just using the Newton's second law in the inertial reference frame. Okay, so then what we have left is this okay, so I'm going to do a slight switch here. So by switching the order of this cross product, and this cross product we can flip the sign here. So that is, we have R dot in S prime crossed with omega, and then we have a plus m omega. I'm going to do the same thing here. I'm reversing the order of this cross product. Okay, so that is Newton's second law in the rotating reference frame. So ma equals F, so the real forces plus 2 pseudo forces. So this pseudo force is the Coriolis pseudo force. This one is the centrifugal pseudo force. Okay, so that's where I'm going to stop. And you can use this equation to do 9.20 in your homework.